Hello students, in our last class we have started the second chapter of physical chemistry, that is solution, and we came to know about the important different concentration terms related with it, and we have seen the numerical as well. Okay. Now today we are going to see the solubility of gases in liquid. That means how a gas is soluble in liquids. Gases are completely miscible with each other. As we know, gases can mix with each other. Gases also dissolve in liquid and solids. For example, soft drinks like Coca-Cola and Pepsi contain carbon dioxide dissolved in water under very high pressure. Oxygen is sufficiently soluble in water, and aquatic animals and plants use this oxygen for their survival. As we know, gases also dissolve in liquids, and an important example of the solubility of gases in solid is the solubility of hydrogen gas in palladium. So now today we'll focus more on solubility of gases in liquids. Say for example, we have seen the diagram over here. In the first diagram, we have got the liquid. We can see the solvent at the bottom, and above it we have got gas. Say for example, you can take the water, and the gas of that will be water vapor. Okay, now, and again we have got the same kind of figure, but here there are some changes that I'm going to explain. Say for example, in this liquid or a solution, we have got the water molecules, and we have got the gases molecules above it. And over here we have got a piston, so we can move up and down. That means we can increase the pressure as well as we can decrease the pressure. Now what will happen, what we have done is we have just moved this or applied more pressure than P1 at this. So what will happen, the piston will shift down. In doing so, what will happen, the gases molecules will come closer to each other. Now when they come closer to each other, what they will do is they will try to strike the molecules, the surface of the liquid, and some of them, because of their compressed nature, some of them will try to dissolve in this solution. So we can see that when you increase the pressure, the volume of the gas decreases, and if we have got the liquids, then that gases molecule can be dissolved in it. So this is how we can see that the gases are soluble in liquids. The same things that takes place in the cold drinks and all. The gases molecules are compressed at a very high pressure so that they will dissolve in the liquids. Now, based on this, we have got one very important law, that is Henry's law. Now let us see what is this Henry's law. Because Henry's law gives a relationship between the solubility of a gas. Now over here we came to know that the gases molecules are getting dissolved, or they are getting soluble in the liquid. So Henry's law, after the experiment, he gave the relationship between the solubility of a gas in liquid and its pressure at a given temperature. So according to him, the mass of a gas dissolved per unit volume of a solvent is directly proportional to the pressure of the gas in equilibrium. That means whatever mass of gas dissolved in per unit volume of a solvent is directly proportional to what amount of pressure is applied in equilibrium with the solution at a given temperature. Say for example, mathematically, M is proportional to P according to this statement, where M is the mass of the gas dissolved per unit volume of a solvent, and P is the pressure of the gas in equilibrium with the solution. So since M is proportional to P, when you remove this proportional sign, we put some constant, let that constant be K over here. Okay, constant K. So we can remove that proportional sign and we can put equal to sign. So once again we can just change this, we can take this P down, so it will be M by P equals to constant, okay, where K is the proportionally constant and it is the characteristics of the nature of the gas. Then you'll find that when that is for one gas molecule, but when you have got a large number of gases that are dissolved in a liquid, Henry's law is applicable to each of them separately as in the case. So the mass of each gas dissolved is directly proportional to its partial pressure, we can say. Dalton, a contemporary of Henry, also arrived at the same conclusion independently, that is Dalton's partial pressure. The solubility of gas in a liquid in a liquid solution is proportional to its partial pressure. Okay. Now, over here, say for example, if X2 is the mole fraction of the gas in the solvent and P2 is partial pressure, then according to this statement, the solubility of a gas is proportional to its partial pressure. So we can write X2 proportional to P2. Okay, so over here we have removed that proportional sign by putting constant K dash, and once again over here, if you take this down, it will be 1 by K, and 1 by K dash has been replaced by KH. So simply P2 will be equal to KH into X2. Okay, where KH is called as Henry's law constant. Thus, from this statement, we can also define Henry's law as the pressure of a gas over a solution in which the gas is dissolved is proportional to the mole fraction of the gas dissolved in solution, because this is the mole fraction of the gas. So this is the second form of Henry's law. Now we are going to see limitation of Henry's law. What is its limitation? Henry's law is valid only if, first, pressure of the gas is not too high. The second is the gas is only sparingly soluble. That means it should be only less soluble, we can say. The temperature is not very high. Number 4, gas does not enter into chemical combination with the solvent. That means the gas should not go under chemical reaction with the solvent. And number 5 is gas does not dissociate or associate in the solvent. That means it does not also apply to the to such kind of gases which will dissociate, that means break down into ions. That are the limitations of Henry's law. Now we will see the application of Henry's law, which are very important. That means where it is applied. The first application you will find in the